Hello and welcome back to ISOmath. Today we're dealing again with the unit circle and we're talking about special points on the unit circle. In this case, we want to find out the endpoint that corresponds, this endpoint here, that corresponds to an angle measure of 30 degrees. And what we can do is we need to draw back from our good old geometry days. So in our geometry days, you can see here that if I have that endpoint, I essentially can form this triangle here. Not only is it a triangle, but more specifically, it's a right triangle. And this right triangle has a measure, obviously, 30 degrees here. With this being 90, we know that this internal angle here has to be 60 degrees because all triangles have a total of 180 degrees. So we have dealing with a special case here, which is a 30, 60, 90 right angle triangle. So this is how we go about solving that problem. So we want to find out this triangle. We know that this particular side right here has a length of 1. Reason being, we're on the unit circle, and the radius, this is nothing more than a radius of the unit circle, so it has a length 1. What we're trying to find here is this distance from there to there, which corresponds to the x-coordinate, and we need to find this height of the triangle, which corresponds to the y height on my axis. So if I take that triangle and bring it over here, I'm dealing with a normal 30, 60, 90 degree triangle here with a value of 1. Well, the way we come about solving this problem is the ancient Greeks had an ingenious idea, and this is what they did. They simply reflected this triangle over its axis here, the x-axis, so it looks something like this. And by reflecting it, I basically have two congruent triangles. This angle is also 60. We know this one to be 90. I'm sorry, this one to be 30, this one also to be 90, and down here also to be 60. So I've simply reflected the triangle over itself. But the interesting thing now is if you look at the big triangle here, I now have an internal angle here of 60 degrees, 60 degrees, and 60 degrees. So I've now formed an equilateral triangle. And we know properties of equilateral triangles, not only are the three internal angles congruent, but so are their sides. So this now has a value of 1, as well as this entire length here has a value of 1. Well, if that has a value of 1, and this is simply reflected about itself, we can break it down, and we know that the smaller value is nothing more than 1/2. So from here to here, we know we have a value of 1/2, and from here to here, we have a value of 1/2. So now if I go back to my original triangle, it'll look something like this. And now noticing that I have a right triangle, I can use Pythagoras' theorem, which simply states that a squared plus b squared equals c squared, which is simply one leg squared plus the other leg squared, is equivalent to its hypotenuse squared. This is the hypotenuse, this is one leg, and this is the mystery leg. So we'll call this side A, we'll call this side B. So we know that 1/2 quantity squared plus b squared is equivalent to 1 squared. And going through simplification, that gives me 1/4 plus b squared equals 1, or simply b squared equals 1 minus 1/4. So we know that b squared has a value of 3/4. And taking the square root of both sides, so we know this b length has equivalent value of square root of 3 over square root of 4, which is essentially square root of 3 over 2. So that is and in this case, this b length, if I look at the big circle, this a value right here corresponds to my y value, so that's going to be 1/2, and this b value right here corresponds to my x value, so this has a length of square root of 3 over 2. So the triangle here, the 30, 60, 90 triangle, has a hypotenuse of 1. The side opposite of 30 degrees has a value of 1/2 on the unit circle, and the side opposite of 60 degrees on the unit circle has a value of square root of 3 over 2. This will always be the case on any unit circle 30, 60, 90 triangle. The side opposite the 30 degree angle, the small angle, will always be 1/2. And the side opposite of 60 will always be square root of 3 over 2. So ultimately our endpoint here has an x value of the square root of 3 over 2, and a y value here of 1/2. So the endpoint that corresponds to a 30-degree angle on the unit circle has the coordinates of square root of 3, comma 1/2. Now let's take a look at another example. Now let's find the endpoint that corresponds to an angle measure of 60 degrees on the unit circle. So we're looking for that endpoint. Well, we're going to do the same thing here. We're going to drop down a perpendicular line, and essentially with this line, and this forms a right angle here. So if this is 60 degrees, then my other internal angle has a value of 30 degrees up here. So again, I'm looking for this x length here, and I'm looking for this y length there. And that'll give me my matching x and y coordinates. We know that because it's on the unit circle, I have a hypotenuse of 1. So I take this right triangle out, and it looks something like this. And when I take it out of the circle, you can see that this is, again, nothing more than the 30, 60, 90 triangle that I dealt with before, just rotated slightly. And as we figured out before, we can use the same principles, but essentially we know that now, from the previous example, that the side opposite 30 degrees on the unit circle has a value of 1/2. And the side opposite the 60 degrees has a value of square root of 3 over 2. So putting that together, I can go back and find out my x and y coordinates. They are now, my x coordinate here is going to be 1/2, and my y coordinate is going to be the square root of 3 over 2. So I'm left with an x and y coordinate of 1/2, comma square root of 3 over 2 as my endpoint right there. And you're going to see this pattern repeat itself throughout the unit circle, which we are going to continue to explore. Hope this helps. And remember, check back to ISOMath for all your math needs, and we'll see you soon.